Just to convince you that this roll of thread actually moves as I say. So you pull him here and now he moves towards me. Little sliding, let's see, here we go, yes. Yes. If you lift the angle, of course, then you can make him roll out. But when you have it horizontally, he will always go towards you. So if you want to play around with it, be my guest. Okay, we continue with chapter 3, and now we will look into what is called junctions. Junctions, they are very simple. They are either 0 or 1. It's talk about how different elements are connected together in your problems, in your machine, in your whatever. So junction, as the book does it, little complicated, but we jump here. They have a generic J that can be either 0 or 1. Never mind that. We can jump directly to them, but the first rule that is important. These junctions, they are totally passive. They don't use energy, they don't create energy, they don't store energy, so they are completely ideal, as we call it. Junctions, no loss or gain of energy. That's important. So that means when you have a junction here, and then a junction, he can combine many of these power bonds. Some may go in and some may go out of this junction. The direction there, that's up to us. What we means is a positive direction. That's not so important. But what is important is when you make a sum of all the powers entering and exiting, you will always get 0. So no loss, no gain of energy. That's the important part. So we start with the 0 junction. And then you can draw as many bonds as you like, hitting this 0 junction. Have one coming in here, another one coming in here, and then we have a couple that exits, maybe something like this. And now the only interesting part for a 0 junction, that will be the different flows that enters him. For any bond, you will actually always write effort and flow, always. And here, when you have many bonds, you will name them, so maybe 1 and 1. But around a 0 junction, it's also called a common effort junction. That means all these bonds, they have the same effort. So you don't have to, well, if you call him E1, that's your choice, then it's the same effort on all these bonds. But the junction, the flow can be whatever. If I have Q1 here, then Q dot 2, Q dot 3, and Q dot 4, something like that. And now, if you look at, say, the power that comes in, power in, that will now be F at 1, Q dot 1, plus, that's the power from bond 1 in watt, plus the second one, he also goes in. So here, the direction of these half arrows, they tell in or out. So here, well, the effort is the same, but Q is now number 2. That's what comes in. Has to equal power out, which then is F at 1, Q3 dot, plus F at 1, Q4 dot. And there you see now the F at 1 is all over the place. So you can divide by F at 1 and then just see then sum of all the Q, all the flows, Qi, see, sum of all i's is equal to 0. So in other words, what flows in equals what flows out. That's a 1 junction, sorry, a 0 junction. 0 junction, also called 0, also called common effort junction. And in a bond graph, to make it simple, typically you won't write all this effort 1 on all these bonds. But you could use either a superscript or a subscript or something around this 0. Here somewhere, just write E1. So that means all the bonds connected to this junction will have the same effort. That's all. So that was 0. Any questions to him? Is that okay? For now it's a little abstract. It will be easier later on when we have some examples. But let's just take the 1 junction first. One junction, also known as common flow junction. So here you have a 1 junction. And again, you will draw some bonds that somebody hits him, enters the 1 junction, and some bonds that will exit him. Like this. And now the flow will be the same on all these bonds. So instead of writing the Q dots on every bonds, you can write one single Q dot here and say, this is the flow that is the same on all bonds around this 1 junction. But the efforts, they can be whatever. So here we have F at 1, effort 2, effort 3, and effort 4. So we will have the same here as with the zero junction. When you now use the sum of all powers entering the one junction and all the power exiting must be equal. No loss of energy, no production of energy. So here the sum of the efforts equals 0. Algebraically, now this means that when you have a one junction or a zero junction in your bond graph, they will result in one equation, one algebraic equation. So you have the summation rule around a one junction. Sum of the effort has to be 0. Or around a zero junction, the sum of the flow has to be 0. So it's just one single equation that comes out of this. Some equivalences here. Easier to look at some examples before we go to those. So let's try, what should we start with? We start with the mechanical domain. Should be the simplest one to picture the different junctions here. Mechanical, one junction. So say you are using a force F hitting a plate. This plate on the other side is connected to here, say a damper like this, and down here another damper, and here a solid wall. These dampers we will call R R, B. So that's just linear dampers, linear resistance. No problem there. And of course, when this force acting on this plate is strong enough then that he can move this plate, we will only have this position and the velocity x dot that is our unknown in this problem. If we know x as a function of time, we know everything here. So sort of a one-dimensional problem. Now make a bond graph of this problem. How should we now think? Well, I have this solid plate here. He can move back and forth. So this plate, he will now be, say, the same motion for anything that might be hooked up to that plate, that object. No colors. Okay. So when the motion sort of is given, and here I have at least a force hitting him, and here a damper, and here another damper. How should I write this? Well, what should it be? What kind of junction is this? Well, for all these connections, all these different elements connected with him will have the same motion, will have the same velocity. Hence, this is going to be a one junction. They have the common flow, they have the common motion. So here I will have a force acting, that will be a source, and then he will split, hitting one resistance and another resistance here. And that's it. So the unknown that will sort of describe my problem, that will just be the velocity x dot. I can write it like that. Mark this one junction. And what's now interesting will be the different forces acting on these two resistances. This source, he will be a force. What kind of source is that? Well, that is an effort source. So then you will write S effort. So here the effort will actually be the mechanical force in Newton, and the flow, well, that's given by the x dot, which is the same on all these three bonds. So now for this problem, to solve it, well, of course, it's then a question of finding the force Fa here and the force Fb here. How will this force split up? You know already, around a one junction, the sum of the effort has to be 0. So here I can write immediately this force hitting the plate will be split in two parts, Fa and Fb, of course. So that will be a mechanical one junction for you. Everybody with me on that one? Yeah, we will have more examples of these later. Let's just take another example. Zero junctions together with a mechanical problem. So again, I have a force. He hits one damper directly. Here, damper, and that spot, RA. And then you have another point here, moving with a different velocity, hitting the second damper, RB, before finally we have a solid wall. Now what? How should we describe this problem? The first, in such problems, actually try to identify points that have its own velocity. So here we have one point, or this part of the damper, he will move with one velocity. Here we have another part, actually everything here, and this part is standing still. So we have a couple of parts here moving. But if you look at this damper here, he will have one force acting on one side, but he will have exactly the same force acting on the other side. So for such a damper, to include him in a bond graph, here you will use a zero element. So you will have one force hitting him from the left. That's the effort source. And then we hook up this element. And then we continue with another zero junction, and then we'll have the next damper, and then finally you have a solid wall. What's a solid wall? Well, that's something that has its own unique velocity. So there typically you will use a one junction to describe a solid wall. But here you can now start to simplify, because a solid wall, he doesn't move, hopefully. So the x dot, the velocity here is 0, meaning the flow here is going to be 0. That means you have no power entering the wall. So this bond hitting the one junction can be removed. So you can forget about the wall. Then the bond graph is left with these two zeros. And when you have two zeros next to each other, you can actually just join them. That will be the same as just using one single zero junction. So the same we could have done in such a problem if we had another one junction connected here somewhere. We could just have joined them. So this bond graph can be simplified to something that looks like this. Effort source hitting 1, 0. So you will now have resistance A, RA, and resistance B. And when you have two resistances like that, well, you can simply just sum them directly. So, but for now, we just leave it like that. Yes, so it's possible to do simplifications. We will have a lot of these rules how to simplify a bond graph, but already now you should sort of have the idea what's going to happen. You have your physical layout of your problem. This is where you start. Then, using bond graphs, you will identify different elements, zero junctions, one junctions, resistance, inertance, springs, and then you will remove the physical image and just be left with a graphical representation of the real problem. And then you continue here with the problem. Now you are sort of leaving the real world, just playing around with these graphical bond graphs. And then we simplify and tricks and do some working procedures before we finally end up with the differential equations that can describe the problem. That is what's going to happen. And now these junctions are sort of an essential part of this process. How you hook systems or elements together physically in a problem. We have a lot to cover here with different examples, so it will be more many examples here before you are comfortable by doing this yourself. So like this one, for instance, what should we do here? Force attacking a mass. Then we have a mass number 2 hooked directly to the first one. And here we have a spring, and here we have a damper. And then a solid wall. How should we do with that one? Well, let's see. Start with the force here and the first mass that he hits. This mass, so it's a big lump, he's moving with a distinct velocity. So to describe this motion, I need a one junction. One junction, that was the common flow, the common motion. So I will start with an effort source hitting a one junction. This one junction has some mass attached to it, mass number 1. So immediately I can hook up a mass number 1, I1 or small m1 if you like. Normally you will always use the generic symbols in the bond graphs. You will use I for masses or inertances. You will use C for springs. Not small m and small k, but always the generic symbols I and C and so on. Okay, let's continue. Here, this physically, it has 3 branches, 3 bonds that exits to the right of him. So it must be 1, 2, 3. Now this one, start with the easy one, M number 2. He's hooked on directly. Of course, you could have another one junction there to describe the motion for number 2. But of course, these are connected solid. So if one is moving, the other one is moving together with him. But okay, for now, let's just do it step by step. So he has sort of his own one junction. And then I hook up a mass on him as well. So here comes I number 2. Of course, you can simplify here. You have two one junctions next to each other. So if the flow is the same here, well, it's the same flow on both of these one junctions. So you can remove the last one I draw there. Here, I will now have a spring. How do I insert a spring here? Well, I have one force hitting the spring from the left, but you will have the exact same force on the right. So same forces on both sides, that's the common effort. Then I use a zero junction and insert a spring here, a C element. Then I continue and hit a wall. Okay, continuing, hitting a one junction where x dot is 0. A little bit training, you will never draw these at all because you know it's a 0 power on a solid wall and it doesn't move. So, but for now, let's just do it anyway. Same now with the damper B down here. Same force on each side. Then we insert him using a zero junction down to a resistance. And then we continue hitting a solid wall, which is not moving. This will be what we call the raw bond graph for this example. I'm not sure if the book has done it so thoroughly. No, he cheats a little bit. Goes a little too fast. Let's see if we can get there. So this is what we then call a raw bond graph. And now simplify. So you will have here a long list of rules how to simplify a bond graph. And one simplification, remove all the bonds that has 0 power. So here, when the flow is 0, then the power has to be 0. Even though you have a big effort here, a big force hitting the wall, but the wall is not moving, you don't do any work. So this one can be removed and this one can be removed. Then these zero junctions, they can also be removed because you have only two bonds for a junction. Then it's not a junction anymore. Then you can just remove him. So the first simplification, effort, source, hitting a 1. Well, let's see now. We removed him, we now remove him. And also this one junction can be removed. There's only two bonds. Then we have I1. We have a C. We have I2, and finally we have R. And now another simplification. We have two masses attached to the same one junction. Of course, we can just join these two masses together. So the final version will now be total mass here, which then is the sum I1 plus I2, C element and an R element. So this is sort of how we are going to use a bond graph. Start with the real physics, a raw bond graph, simplify, simplify, simplify. Finally, you have a very cute bond graph, which is then very easy to analyze. hopefully. This will be easier the more examples we get. We have some stuff to cover here. For now, let us jump to exercise number 2. Should be out here somewhere. So, some hints to exercise number 2. So here we have a motor connected to a fan. We have a gear here. The radius from the wheel on the motor is smaller than the radius for the wheel on this fan. So here, definitely, clearly, we are talking about an ideal machine. We have given the motor, the characteristic curve of the motor, and also for the load, the fan alone, in this torque rotational speed diagram. And you have even been given the different data values. So here you can use cut and paste directly in MATLAB, so you don't have to punch these numbers. That's convenient. So clearly here it's going to be an exercise using a lot of inter-P1 interpolation to create these curves nice and smooth and continuous. For this system here, what's going to happen when you have both a motor and a fan and you switch it on t equals 0? What's going to happen? Well, t equals 0, you have no rotation. Everything is standing still. But your motor is pretty strong, much stronger than the load. So this net torque is going to speed up the system. It's going to start to move, and it's going to rotate faster and faster until you hit this point. Then you sort of be in balance. Then all the power out from the motor will be swallowed by the fan. It's sort of in balance. And also this is what we call the stable operating point. But it said in the text, this motor is going to burn down if you leave him running for a long time with a torque larger than 4. So you can't do that. This is going to be too heavy. So the maximum should be 4. So this should be the operating point for the motor, not this one. So here clearly we have to use a gear to change the parameters. The numbers here, they are given in some inches and pounds, and also here RPM. You don't have to worry about that. You can use the numbers directly. You don't have to rewrite them into SI units. So that shouldn't be a worry. For the exercise, I have some questions here about bond graphs. Draw the bond graph for this system, and draw the bond graph and draw the bond graph and simplify and so on. Don't worry too much yet about the bond graphs. For this, we haven't learned so much about it yet. So don't worry about the bond graphs, but try to do the rest of the questions for the dynamics in the problem, and also the simulations and the programming. Some trick I can show you. Of course, the first one, you had a motor, and then small wheel, bigger wheel, and then you have the fan here. The bond graph here you can draw fairly straightforward. It will be a source hitting, and it's no secret, it's going to be a transformer, because you have a direct coupling, rotational speed here. If you know the radius ratio here, you will know the rotational speed on the other wheel. Hence, it is a transformer, it's not a gyrator. And on the other side, you will have the load, the resistance from the fan. So that will be actually the entire bond graph for the first part in the problem. The next part in the problem, that is a little bit more tricky. Well, we can do it now. We insert rotational mass for the motor, some parts of the motor that is spinning, and then also for the fan itself. And the fan, well, that's quite heavy. The motor, not so heavy, but still we include it. So here you have some rotational part in the motor that has mass Im, and then the rotational part for the fan IV. How will the bond graph look now for this problem? Well, it's going to be a little bit more complex. We have the source, and now remember the source here, it's not an effort source, it's not a flow source, it's a real source. We have the characteristics for him, the coupling between torque and rotational speed, so it's a real source. And he will now hit something here that rotates with its own velocity, with its own flow. So that's a common flow junction, a one junction, common flow. So the rotational speed here, what should we call him? Phi dot number 1, for instance. That is the rotational speed for this part of the problem, just for the motor itself. And these rotational parts, they have mass. We hook up here directly. Then we continue down here. Then we have to go through the transformer, through a gear. And then on the other side, we find a totally different rotational speed. Another one junction with a rotational speed phi dot number 2. And here we have two things. We have a mass, yes, of course, IV, but also the load, the total resistance to rotate this fan will now enter into the problem. So this actually will be the bond graph, the answer to this part of the exercise. So now I actually have done it for you. Draw this bond graph for the system. A little hint further. You need to simulate here, so you have to program this process. Well, solving this one now will not be easy for you guys. For these masses, you will have one equation. For the resistance, we have one equation, a coupling between effort and flow. For the one junctions, you get one equation, one algebraic equation. You sum all the efforts around the one junctions to get 0. For the transformer, you will have two equations. So all in all, a whole bunch of algebraic equations. That will be one way to solve the problem. For us, now we can cheat a little bit. First of all, if you look at the graph up here, what is interesting here for the dynamics of this problem, in this part of the problem, if anything is to change, then you don't have a balance between the driving force in the problem versus the resistance. So if I now rewrite the problem like this. So what should we call this one now? Net torque. I just subtract these two and say the difference here, that is what I have left to change this system. And now you see on the other side here, it's now possible to simplify this a lot. First of all, this one junction here can now be removed since he has only two bonds. So he doesn't do any good anymore. It's the same flow on these two bonds. Well, then the effort has to be the same as well. So he doesn't do anything. Then he can be removed. And then we are given a cute little trick. When you have a transformer and then a mass and inertance hooked directly into him, you can simplify these two by an equivalent mass, where this equivalent mass equals the transformer value squared multiplied with IV. So now you will have something looking like this. S minus R hitting the first one junction, Phi1 dot IM, and this one now will be T square IV. So it's a little strange way to think, but this is sort of the mass from the fan, the rotational mass from the fan that the motor feels after this gear thing has been coupled in. So it's a very neat way to simplify it. And then finally, you have two masses hooked on the same one junction. Of course, you just join these two masses together. So the total bond graph will now be, well, a one junction, which actually you can remove, hitting IM plus T square IV. So this will now be the total mass that the motor feels that he has to spin up. And finding a differential equation for that is not so hard. Then you will have the net spin will be the the net torque will change the net spin of the system, where this will now be the total moment of inertia. So there will be possible to get guidance on exercise 2 already now on Friday, but also the deadline was set until next week, I think. So you still have plenty of time for it. We will do more examples with bond graphs, junctions, inertances, compliances next week. Any questions from you? Okay, then we stop here.